Welcome to the next episode of our Cleantech Conversations. My name is Alexander Wemme. I'm Vice President Energy Conversion and Storage at ARDENNE, and we are here at the hy-fcell in Stuttgart with two partners from partner companies in the German fuel cell corporation, Frey and Jochen Kober. Our topic is hydrogen, energy source of the future. So it's quite an ambitious title for this conversation. Energy source of the future, strong words. Jochen, what is making hydrogen to be so important for the energy in the future on our planet?
So, state of the art is producing hydrogen by reforming natural gas with a steam process with the disadvantage of producing carbon dioxide. Looking on the globe, the main producers of natural gas are the United States and Russia. This situation is having a major geopolitical impact on the economic and security situation of the Northern Hemisphere, especially in Europe. So hydrogen production could help us in different ways. The global distribution of hydrogen needs an efficient economic production and transportation, and on the other side, consumers with a high demand. Which regions would be able to produce such huge amounts of hydrogen out of renewable energies? This could be the Northern Hemisphere, this is coastal regions with wind energy, and on the other hand it could be, for example, South Africa or Australia with the solar energy.
And looking at the globe, do you see already programs that are there in different states that support hydrogen?
Yes, in the United States, for example, the Inflation Reduction Act, and they invest a lot of dollars, billions of dollars to push this forward. And in Europe we have the Green Deal, and since 2020 the hydrogen strategy for a climate neutral Europe.
If I remember the experiment from school, Thomas, there was oxygen and hydrogen making a big explosion, or at least a buff or a boom, but there was no color. Hydrogen was a sort of invisible gas, but people are now talking about different colors of hydrogen. So can you maybe talk us through that a bit?
Yes, I can. It's funny also you asked me, because I'm trained chemical engineer. So the color of hydrogen obviously is neutral, so it's no color. The color scheme has been introduced in the light of the greenhouse gas occupation, and so you distinguish, for example, starting from the brown hydrogen, which is produced out of coal via burning coal. And the next is, that's the prominent one you already mentioned in your bit before, the grey gas, which is produced just from burning natural gas resources. Obviously the problem there is the CO2 which is produced in that process, so it's called grey. And now we come to the more brighter colors, because the more brighter colors indicate it's environmentally better, or for the greenhouse gassing better. So you have the blue hydrogen, which is like the grey, starting from a natural gas, but you solidify the CO2 which is emitted there, and you store it, so you take it away out of the process, makes it the blue hydrogen. Or the green hydrogen is if you have renewable energy coming from PV or coming from wind, and you use this energy in electrolysis to produce hydrogen. There are other forms. There is the pink one, including nuclear gas. There is the yellow one, which is pure photovoltaic. So there is even more distinctions, but these are the more prominent and lookable at. And out of that, I think we will have a look into more the green hydrogen.
Yeah, I think looking at green hydrogen really is important. So hydrogen, as you said, generated via electrolysis. So a process that sort of separates water in the hydrogen and oxygen. There are a lot of discussions and announcements globally. So what are the volume projections that are forecasted for maybe 2030 or 2040?
In a way, this is really funny, because we are now at 2024, and at the moment the current measuring in energy, the current production of hydrogen is at around 5.5 gigawatts worldwide. EU has stated its goal is up to 2030 to go up to 40 gigawatts. That's only the EU. Yeah? And worldwide we speak, depending on the forecaster, between 100 and 600. So imagine we need to 8 to 25 times increase in a couple of years the production of hydrogen, green hydrogen. So there is a major work to be done. More initiatives need to follow.
Yeah, that's true. I mean, impressive numbers, and the ramp up is almost unbelievable, right? Me, myself, I've been to dozens of electrolyzer companies with more than a decade of experience in the automotive industry, you know. Looking at it, the production processes don't really seem to be mature and not really industrialized, what we would need on multi-gigawatt scale. So, Jochen, what are the main electrolyzer technologies? Because I think there are a few around. What are their advantages, disadvantages, and maybe what's their maturity, right?
There are main 4 technologies to mention. We have one technology, it's an alkaline electrolyzer with a fluid electrolyte, and we have 3 kinds with a solid electrolyte. To mention is one of them is a proton exchange membrane electrolyzer with a very dynamic curve, and you can use this one especially for the wind energy and the solar energy, because they are fluctuating, and this is very possible to know. On the other hand, we have a solid oxide electrolyzer with an efficiency of about 90%, but it's a very slow one, and you need a very high temperature to work with it. To mention also is the critical raw materials. At a proton exchange membrane electrolyzer, you need very expensive materials. So maybe the alkaline is the working horse of our production of the new hydrogen we need.
Thanks for the overview, Jochen. Well, as far as I see it, really nothing is completely mature or industrialized, and it's also hard for those green technologies to compete with conventional, as Thomas explained it, for example, gray or black or brown fossil-based hydrogen production. So in terms of cost, levelized cost of hydrogen, LCOH as we call it, where do we need to be? What are the cost targets?
Topical, it's about $20 per kilogram for small amounts of hydrogen you have to use, and in the state-of-the-art production price of natural gas, it's going up to $4 to $5, and the target cost for about 2030 will be $1 to $2 per kilogram. And in the USA, based on the IRR, there will be $3 production subsidy for each kilogram of hydrogen.
Okay, well, I mean, cost-wise, comparing $20 to $1 or $2, even subsidized or not, it really sounds ambitious. Do you think it's realistic, Thomas, that can be achieved?
I think it can be achieved, but we need to really have 2 things. We need to look at the scale effects, and this is a little bit a chicken and an egg situation. Yeah, we need to have more of electrolyzers produced so that we can bring the costs down. So you have the typical scale effects. We have seen that in the fuel cells, that the cost of a fuel cell bipolar plate came down to roughly $1 per half plate at the moment. So this was only possible by scaling up to the millions. The second part, which can be done in electrolyzer, must be done, is there is a lot of precious material in the cost factor. You need platinum for the transfer layers. You need coatings. You need the proper initiating agent, and there alternatives need to be found, more cheap alternatives, because precious metals are precious because they cost, and they are also hard to get. So there is a lot of space there for cost reduction. So I think yes, that can be done, but we need to accelerate scaling and the production.
Yeah, you're right. I mean, iridium as a catalyst and the anode side in the PEM electrolyzer, enormously expensive platinum gold coatings that we see on bipolar plates in PEM electrolysis. And yes, I think things can move forward and costs can be reduced, basically in the stacks. But if we assume we have sufficient supply of green hydrogen at a certain point in time, at a competitive price, then we need to look at the applications, right? And I think first of all, for example, fertilizer will be converted from grey hydrogen to green hydrogen. Then we need to decarbonize heavy industries like steel or glass production. Chemical industry, I think green hydrogen can be used. And I think at the very far end, not at the very beginning, we are also talking about mobility applications, where we could either burn the hydrogen as a direct fuel in internal combustion engines. We can create synthetic fuels or e-fuels as they are called, or sustainable aviation fuels for flying, still use them in combustion, or ultimately we can use the hydrogen, green hydrogen ideally, in hydrogen fuel cells. So Jochen, if we look at mobility and the hydrogen fuel cell, and we look at ranges and vehicle classes, where do you see as the sweet spot? What is the ideal use case for a hydrogen fuel cell?
I agree with you totally. First economic use cases will be in heavy duty and long range applications like trucks, mid-range aviation and ships. And one bullet point is energy, density and range. Battery vehicle versus fuel cell vehicle, there's nearly a factor of 4 when you look at watt-hours per kilogram.
So Thomas, you talked us about the enormous sort of growth potential and sort of demand we have on the electrolyzer side. For the fuel cell, is that similar? What growth rates do we need to expect there?
Well, you have to distinguish between the growth rate, which is the time, how long it takes, and the amount it will pick up. The time is a little bit uncertain, so difficult to really say how long it takes. It depends on the cost of the hydrogen. It depends on the availability on refueling stations. But there are some numbers out there. We think that by 2030 we will have around 13 million cars. If that is true, 13 million fuel cell vehicles. If we break that down with an average amount of 300 to 350 bipolar plates, we are talking about an amount of 4 billion bipolar plates which need to be produced for this number. Now, our machine, laser welding machine, currently makes around 4 million per unit. So that would mean that we would need 1,000 welding machines for these 4 billion plates. Now it may be that these 4 billion plates will not be at 2030, maybe it will take a little bit longer, but there is definitely a pickup, and when it picks up, it's going fast upwards.
But if we look at those volume projections, I mean, what does this mean, Jochen, for the cost level of the fuel cell system and the fuel cell stack? Where do we need to be?
There's a big difference when you produce 10 fuel cell stacks or 10,000. In this example, there might be a cost breakdown of 20% down when you produce 10,000 fuel stacks. And 10,000 fuel stacks, this is about 8 cruise ships or 10,000 trucks, for example.
Okay, but it's not only the increase in volume and the challenges, but yeah, Thomas, you already mentioned it's scaling. It's a totally different level of industrialization that we need to see. I think that's well known to the automotive industry with other components, maybe not for the fuel cells yet. So in terms of scaling and the volumes, what does this mean for production equipment, for the machinery that's going to be needed? Is that comparable to like gigafactories in the battery cells, or?
I mean, speaking for the bipolar plates, which are at the core of the fuel cell stack, speaking of them, yes, of course. If you look how many, as I mentioned before, how many bipolar plates you need for one stack. So we have customers, they look for a cycle time of 1 second, meaning they are now looking for machines which produce 1 bipolar plate each second. Throughout the whole chain, from stamping, including leak testing, up to also coating. 1 bipolar plate per second. So there is a lot to be done and worked. So there will be gigafactories because the amount is so high of bipolar plates which are needed. The rest is comparable with the rest you need in a fuel cell car, which a balance of plant parts is comparable to what we know now from the combustion engine world. It's handleable, but bipolar plates is because it's factor 300 to 350 in one stack. It's just an unbelievable scale up, and we need machines which are capable of putting out each second 1 bipolar plate.
Yeah. I mean, all our 3 companies that we represent, we are equipment manufacturers, right? As we all know. So for the overall process chain, not just of the stack, but also for the bipolar plate, which is just one subcomponent in the stack, it's a fairly complicated process chain. So I'm just wondering, how do you really build up integrated production lines? And what does this mean in terms of cooperating and collaborating with our customers? Jochen, what's your take? What does this mean for us?
This means creating new standards and process parameters during the development process and not before. One question: is the industry and the customer prepared to share a part of the risk with the supplier? In the case of testing battery packs, it was like this, and for fuel cell stacks, customers seek for even more advice and cooperation, which is why we founded the German Fuel Cell Corporation.
Yeah, that's true. I mean, it's not like providing turnkey solutions, but at least knowing what's happening before and after your production step that you're responsible for to provide the best suitable solutions. I need to thank you guys. I mean, if I reflect on that, hydrogen definitely is an enormously interesting topic. Maybe it's hype, maybe it's not, but it's definitely, we need it to be carbon neutral, as I've learned. To me, with automotive experience, it's still a young, partly immature market, but it's promising. And I think Thomas and Jochen, you well explained that the chance is in scaling and industrializing all the processes. So just thanks again, Thomas to you, Jochen to you, and all our viewers for the insights on the hydrogen and fuel cell business.